let's get started. We're recording. So really quick. So actually, Matt, you had asked me a question that I forgot to answer last time about dbScan. Yeah, so if you guys remember, so going back to last week when we were doing the clustering algorithms, dbScan we had, right, that's a clustering based on density. And there's two parameters that we modify with that, which is the number of points that are nearby that would classify something as within a cluster, and also the distance that you look for how far we should look to consider that within the radius of that search group, right? And so that's the epsilon piece, and you were asking about how do we go about choosing an epsilon to start with. Okay, and so there's a couple of techniques, but the most sort of popular generic one harkens back to the elbow method thing. So basically all you need to do is you plot out the points sorted by distance from each other, right? So some points are really close, some points are really far, and you just plot that out. The recommendation is to use the distance at the elbow, at the kink, basically. Yeah, and so that gives you, I don't know, some objective way of choosing an epsilon that's like based on the actual data. Make sense?
Yeah.
Yeah. Okay. And then the other thing I wanted to bring up really quick. Okay, so let me. So I need to correct some things from last lecture. So sorry about the confusion. Very sort of unprofessional of me. There were some things that, I hadn't refreshed myself on before the lecture. That actually led to some confusion when we were talking about the R code. And so actually, I actually did not realize this until looking into it. So when I was talking about support vector machines last time, and we talked about kind of the derivation going from MMC to SVM, we talk about maximizing the margin, right? And so that was like, I showed this objective function where we're trying to maximize the big M, which is our margin. And this actually stems some confusion when we were playing around with one of the central parameters of that optimization, which is C, right? So that cost piece. So the material that I derived that lecture from comes from this textbook, Introduction to Statistical Learning, ISLR. But apparently, that optimization method that they use in ISLR is actually not the common sort of optimization procedure used in most machine learning libraries. So I want to talk a little bit really quickly about what the sort of more common way of doing it is and what the sort of difference is with ISLR, and then kind of why we were getting these weird things happening when we were trying to run the code from last time. Okay, so this is a correction from last lecture. So most ML libraries use a different formulation for SVMs rather than maximizing, maximizing the margin as in ISLR textbook. So what they do is you actually minimize with respect to WB epsilon, the quantity 1/2 W squared. So that's a weight vector plus C I equals 1. And then I'll kind of use the same notation for epsilon, right? And so just as a refresher, epsilon is this slack variable that basically tells us if we are in the margin or violating the margin, aka on the wrong side of the hyperplane. Okay, such that yi wt xi plus b is greater than or equal to 1 minus epsilon I. Okay. So what is W? So you can see here, this is kind of like a vector weight. So this is, if you think of the hyperplane, as a single line or as a plane in 3D or whatever that would expand into in more dimensions, right? This is kind of like the slope in each dimension. And the idea is that, right, so f of x equals wtx plus b equals 0. So this is our hyperplane. So the margin is equal to 1 over W. So before we were maximizing this, maximize the margin, which is equal to minimizing this. And that's why here in this term, it's a minimization of the inverse of the margin as opposed to last time what we were doing, which was maximizing the margin. Okay, and so what is different about this approach? You'll notice our C here. So C is now a penalty. Remember when we talked about C last time, that cost parameter was basically a budget, right? So the larger C is, the more violations that you allow. Whereas here, large C is basically saying slack is more penalized. So it's the opposite. So you can see if I have a large C, but I'm trying to minimize the function, right, then multiplying against the number of violations, you would prefer to have a lower number of violations, right? So this is model avoids violations. And then small c is equal to slack is less penalized. Model allows more violations.
Could you describe again what the margin is?
Yeah. So points on the margin are the ones that are acting as support vector for your hyperplane. So it is the like pillar, it's a pillar point which helps to define your hyperplane.
So the margin is a distance?
Yes.
And within that distance, points are made into support vectors.
Yeah. I would put it the other way around, that if the it's kind of both ways, right? So the points being on the margin is what makes them support vectors, and then support vectors are the thing that define the margin. Yeah. Yeah, so ISLR, so sorry for the confusion. ISLR is the opposite, right? When C is a budget, the large C allows for more violations. So that's why we were seeing weird things happening last time when we were messing around with the C parameter in the function in R. So just know that the sort of proper thing that's happening is that it's following kind of this type of optimization, or we are minimizing the inverse of the margin as opposed to maximizing the margin. The implications being that our C parameter very much is like the same kind of tuning parameter that we've been talking about for lots of other different models, right? So this is our basically allowing for regularization. So who can tell me, large C, you are doing less violations, small c, you're doing more violations. So which one would be making the model simpler and thus avoiding variance, but maybe at the cost of bias? And then which one is making the model more complex, which would help with the bias problem, but lower our variance? Yeah.
Less swag, so less like points that are outside are making it more complex.
You said, sorry.
Allowing less violations.
Allowing
making
less.
The model more
Yes.
complex.
No. Wait.
Wait, if you allow less,
Makes it more complex. How is it related to the model?
So if you think about the hyperplane and its ability to kind of make some of these make the margin basically less linear, right? That has to do with our allowance for the violations. So one more time.
I think like more violations mean less complexity, right? Less violations mean more complexity.
Yeah, which is large C for less. Yeah, that's right.
Yeah.
Yes. Okay.
So large C, less complication?
Yes. Okay. So hopefully that's a little more clear to everyone now. Okay, so we'll move on to kind of the last sort of set of material, lecture 16. Okay, so moving beyond splines and kernels, right? So splines is this sort of semi-parametric approach that is functionally flexible. And kernels we think of as non-parametric. Approach for that's good at finding decision boundaries. So the next logical step that we're talking about, so machine learning approaches as the next logical step. So these are similar in approach to what we've already been studying. But in practice are very powerful at handling scaling. Right, so if we like take a step back for a second and really think about this, you have a set of data that you want to fit some kind of function to, right? And with a linear regression, we're constrained to a particular functional form, right, which is that model has to fit to these things linearly. But you may be interested in all sorts of different functional forms than a linear functional form, right? And so as we evolve away from the linear regression, we started talking about these nonlinear things like splines and kernels. And I hope that you guys are able to see that with a spline or a kernel, really I can already construct a functional fit that could really accommodate any sort of continuous function in any space, right? So what is it about, why do we need to do anything besides a spline or a kernel if I can already fit those things to basically any set of data? And that has to do with, in practice, when you try to do some of these things, splines and kernels can get overwhelmed pretty quickly, right? And what we're going to talk about here is with these machine learning approaches, and one of the reasons why they've caught on to be such a widely used tool is because in practice these things can be applied to much, much larger problems and data sets than splines and kernels have. And that's kind of opened up a whole sort of world of possibilities when we're thinking about doing these this type of data analysis to what's commonly termed as like big data. Okay. Yes.
When you talk about scaling, is that like increasing the number of observations or variables?
Both.
Okay.
Yep. So you will find that the ability of splines and kernels, there's some trade-off there in their ability to handle lots of variables and their ability to handle lots of data in terms of like number of observations. And machine learning is like remarkably, or some of the techniques in machine learning, I should say, are like remarkably efficient at being able to handle both. In fact, that's like literally my next bullet points. So more features and more data. So you'll notice that I wrote features here and that's just our explanatory variables. And data is larger n or more rows / observations. So I'm gonna, this thing about writing features instead of variables, it's because people in machine learning think they're cool and they get to redefine all the terms. So I'm gonna go through some of the machine learning lingo. We're gonna talk about some of that lingo, and really it's just reskinned versions of things we've been talking about all quarter. Okay. Okay, so let's take a look at linear regression, but we're gonna do this in a slightly different perspective. So we're actually gonna build a neural network that replicates what a linear regression is doing. They're called neural networks because they structurally are similar to how neurons act in our bodies, right? Which is you have some kind of input into the cell. There are chemical reactions that happen within that cell that then lead to some kind of output, right? And then those neurons are connected, so you can get these transformations of signals across, many layers of neurons, and hence it's called a neural network. And so let me draw this out to kind of show what this looks like. So we have I1, I2. These are, okay, hang on. Okay, so each of these circles are known as nodes or tensors. And the way these things are drawn, you have stacks of nodes vertically, and then they move and do the transformations horizontally. And each stack of these guys, like so, actually I'll use a different color. Like a stack here is known as a layer. And then, I'll do a different color for this too. So these are known as weights. Okay, so this ends up describing a function f1, I1, I2, right? So our function has two inputs, which is I1 and I2, and that's equal to W11 I1 plus W12 I2 equals L. Does this look like anything to you guys? Yeah, it looks like the equation for a linear regression, right? I could just do beta 0 x1 plus beta 1 x2, or, well, beta 1, I should write it this way. Beta 1, beta 2 x2 equals y, right? So it's the same thing, but now instead of coefficients or betas, we call them weights in ML lingo, and our explanatory variables are our inputs or features. Okay, but they're the same thing. I think on the first day that I introduced linear regressions, we talked about solving for the betas or solving for the weights. And does anyone remember how we solve for betas in a linear regression?
Something over something. Involve matrices.
Yeah, okay. It does involve matrices.
X minus X bar, whatever.
Yeah, so it's beta equals xt x minus 1, and then xty. So I talked about this at the time, right, about this is kind of the standard way we think of solving for the parameters in our linear regression. This is from a closed form analytical solution. It is an analytical solution to the optimization that minimizes the residual sum of squares, right? This is guaranteed the correct solution. And it's fast in theory. Okay. Do you guys remember what I said about solving for betas an alternative way? So, yeah, if you go back to that lecture, one of the things that I had mentioned was that, yeah, most of the time these things are going to be solved this way. But actually, the solution to do this numerically through an optimizer such as gradient descents, so weights are solved numerically through optimizers such as gradient descent. And so you might ask, Alan, why do we do that if you already have an analytical solution that gives you the perfect that always gives you the correct solution and is in theory a lot faster, right? And the reason why we start talking about using optimizers as opposed to doing this, especially in the machine learning context, is because this procedure is not nearly as memory intensive. As analytical solution, or as the analytical method, I should say. So note here you have to do a matrix inverse. That is a fairly memory intensive problem that does not scale well. So if you are dealing with a really large data set that has a lot of variables, this and / or lots of observations, you could actually run out of memory and inhibit your ability to actually solve for the betas. And in the context of machine learning, a lot of the applications are thinking about doing really big data stuff. And so actually, we've kind of migrated back to doing this numerically, right? Or solving this by hand, essentially. Yeah, and so this scales very efficiently. And the application of this is not constrained to a particular functional form, right? So a lot of the optimizers I can actually apply to things that aren't linear regressions, which is going to be very important in just a little bit, as we'll see. Okay, any questions about that so far? Okay, so let me talk about the general concept of these neural networks and how they're kind of structured. So we have our input, and this may be going into a layer, which we may have some kind of transformation, which I'll talk about in just a second. And you may have multiple layers, and each layer may have some transformation on it. These will ultimately go to a prediction, right? So this is our y hat. These might get compared, or you have something called a loss function, which compares your predictions against true values of y. This generates a loss score. And this will go into an optimizer, which will generate weights for each of my layers. Or update weights. Okay, and so you can think of this optimizer. So for example, in the linear regression, this might be my gradient descent, which will be modifying my weights or my coefficients or betas, right, until I can get predictions to go through this loss function and generate the lowest loss score possible. So what is an example of a loss score? Any guesses? Sorry.
Just threw out a number.
Uh,
Loss score, I don't know.
Mean squared error.
Yeah, mean squared error would be an example of a loss score, right? So these are the same things we've been talking about. This is like a metric of determining how good your model is. So like a loss function might be like y minus y, right? And then, or, y minus y squared. Yeah, and so hopefully you guys can see that the concept of what this thing is trying to do is basically the same as what we've been doing all quarter, right? Which is we are trying to minimize what they're calling a loss score, or what we're identifying as the ability of the model to give us good predictions, right? So we want to minimize the error associated with a prediction. And I'm gonna mess around with the weights until I can do that, until I get the best sort of score possible. And that's really kind of what we've been doing this whole time, with different sets of tools, right?
Does the weight update occur for both weights or just for one of the weights to the optimizer?
Yeah, I meant to do this as kind of like a more generic like representation of like, oh, this is the thing that actually gets you your weights, but this is maybe a better representation. It's like the weights get fed back into the transformations until it stops, and then this is like the once it's done, it goes to this final set of weights. Basically, it doesn't need to like keep going, and the way that you decide to stop is if there's some epsilon delta change in the weights, and if they're not changing, if they're changing by a smaller margin than this threshold, then it stops updating, basically.
From the description that from up top, you have the input going into the weights, and that leads to the transformation that inputs to the layer transformation. So like, doesn't the input have to go through the weights first, that then leads to the layer to the layer? That's it.
I see. Because I haven't talked about the transformation yet. Yeah, I guess the more proper way, so the weights and the transformations are happening at the same time. It's like, it's within a layer, you have a function, you have this activation function that does a transformation that has weights associated with it. So it's like, it's kind of happening simultaneously.
Would it be appropriate to say that the output of each layer is multiplied by the value of the weights of the connections between that layer and the next one, then fed into the next layer?
Yes, I think that's right, if I'm understanding what you're saying. I'm gonna manually show an example of like a multi-layer thing, and I'll write it all out, and then I think it will match what you are describing. Before I get to that, and maybe this will help answer your question, let me actually talk about the activation functions, which is the thing that I'm talking about will transform the layer. So if I have something like this, going back to our example, we can actually slightly modify this. So the whole point of a lot of what I've been talking about, right, is this idea of being able to fit these like flexible functional forms, right, that are moving beyond linearity. So we want to think about this as not just linear, but how I might be able to transform or do some kind of transformation to allow it to cover nonlinear space. And the way that we do this, or the way that neural networks do this, is through this thing called an activation function, which is one of the unique aspects of a neural network and one of the things that makes it really powerful. So what we had before, still here, W11, I1, right, which is beta 1 times x1 plus like W12 times I2, beta 2 times x2. But now I'm going to do one extra thing, which is I'm going to make this actually a function, A. So A is the activation function. And this allows for a nonlinear transformation of the inputs at each node. And this is a pretty cool trick. It basically, doing this activation function is essentially going to allow you to, in the same way, or not in the same way, but in a similar way that splines and kernels operate, it's going to now allow me to create a functional fit to any function in continuous space, right? And so I can do this simple thing and actually be able to turn my linear regression into something that could fit any shape that I want. And that is, yeah, one of the sort of powerful things about these neural networks. And let me talk a little bit about how these activation functions work, or what are some common activation functions. So the first one is identity/linear. So if I have f of x equals x, then looks something like this, right? So whatever I put in is actually just going to be the same thing that comes out, and that modification is essentially saying that the function is linear, and that yeah, you don't need to do any other complex transformation on the function. Okay, I can do something like step/binary step. So this would be f of x equals 0 for x less than 0, 1 for x is greater than or equal to 1. Okay, so I have 0 and 1. So here it might be something like this. Okay, so if you guys can visualize this, this means that I can take some set of continuous or even discrete inputs, put them through this neural network, and get what kind of outputs on the other side. Yeah, or I was thinking just 0 and 1s. Can you do multiple category? Can it be discrete? I think it's just binary. No, actually, yeah. If you have multiple nodes in the binary layer, yes, you could do more than 2 outcomes. But yes, you're getting categorical stuff out on the other side.
Shouldn't the function read 1 for x greater than or equal to 0?
Yes, it should. Good catch. Huh?
Less than or equal to?
Greater than or equal to, right? So when x is larger than 0, it's 1. And then when it's less than 0, it's 0. Yeah. We can do logistic, which is f of x equals 1 over 1 plus e to the negative x. That looks something like this, 0 to 1, and you have this sigmoidal shape. Tan h is a common one. F of x is equal to e of x minus e to the negative x over e to the x plus e to the negative x. So that looks something like this. 0. This one's pretty similar. -1 to 1. You go like this. Yeah, so probabilistic stuff for categories are good ways. You could use tanh and logistic. Okay, and then the famous one, the rectified linear units, also known as ReLU. This is by far the most common activation function used. Looks like this. So 0, 0. Let me actually do a thicker line. So it goes like this. Oop. Okay. The rectified linear unit is really powerful because it allows you to have values of 0, which can essentially get rid of nodes that are like not as useful. So it makes your computation much more efficient. You know, when you have these really big neural networks, it may turn out that you don't need as big of an architecture as you've structured, and this lets you get around that essentially by eliminating the input of certain nodes, right? If it gets equal to 0, the ability of the transformation to affect the output is eliminated, and these types of it turns out that all of these transformations, all of these activation functions can allow you to, again, fit into any functional space. It's all about the right context so that you can do it as efficiently as possible. And the fact that, this allows you to get rid of nodes in kind of a smart way is one of the reasons why it's, one of the most popular activation functions. And so most people will start default with a ReLU unless you have a good idea of kind of what your output functional, or if you have some idea about the functional form relationship between your inputs and outputs, should follow some of the other stuff. You might use that instead, but otherwise, most people will start with this. Okay, any questions? Okay. So let's do a slightly more complex example of a multi-layer perceptron. So we call these feed-forward neural networks. So this is a multi-layer perceptron. Okay, we're going to have two inputs going to a layer here. And with these neural networks, every node in a layer is going to be connected to every node in the subsequent layer. So we're going to have something that looks like this. And every one of these edges is going to have a weight associated with it, right? And so this will be W11, W21, and W31. And then that would mean, if we follow that convention, what would I2 to L1 be? Yeah, W12, this would be, not that one. This one would be W22, and this guy would be W32. Okay? And then we'll go to our output layer, P, and so we'll have something like so. And each edge will have a weight associated with it. We're going to use 3 as our, or V, not 3, V as our label. Okay, so here, L1 is equal to, who can help me out here? What would,
W11, I1,
yep,
plus W12, I2.
okay.
Should there be an activation function
A
there?
what?
Should there be an activation function wrapped around that?
Correct. That's why I left a little bit of space right in front. So that's going to be A11. So we'll have our activation function there. L2, okay, so as you guys were saying, same type of thing here. So A12, W21, I1 plus W22, I2. And then L3 is going to be A13, W31, I1 plus W32, I2. And then lastly, what about P? What do you guys think? Yep. So it'll be A2. And that'll be, yes, V1 L1 plus V2 L2 plus V3 L3. Okay? And then I'll note that we've got our input layer, we have our output layer. Everything in between that is known as a hidden layer. So this thing right here, we call this a hidden layer. Okay. So hopefully you guys can see, right, when we've looked at all these other models in the past, we think about x's related to y's, and we have some kind of structure. It might be linear. It might be, these spline things that go through basis functions. And the flexibility of going from my x to my y or my input to my output is usually dominated by, it's usually dominated by the parameter values, right? And the struct, and then we have to come up with these specific structures to denote the like relationship in the functional form between our x's and y's, right? And so the two things that we've really been working with in the past are the parameter values and then what we predefine as our functional forms. Now, if you look at the neural network, we've got a lot more to work with in terms of the things that allow for flexibility, right? Because now, yeah, we also have the weights, and now we have generic activation functions that, you know, can really fit anything, but you're allowing these things to be transformed many times, right? And the number of times that happens is related to what? The number of nodes that we have and the number of hidden layers, right? So before, the way to think about it is you get to play around with weights and the activation functions. And now we get to play around with the weights, the activation functions, the number of nodes, and the number of hidden layers. So you have way more flexibility, right, to arrive at a functional form, which actually, in many regards, is more efficient because you might not have to be fighting against your activation function if the flexibility can be afforded in some of these other dimensions, right? And now it's all about like computational efficiency, right? So I can solve these problems with an arbitrary number of nodes, an arbitrary number of hidden layers, and now the name of the game is really doing it in the most efficient way possible, because, you know, these are really going to be able to go from your input to output in many sort of arbitrary different ways, right? Yeah.
Don't all these new levers present a greater risk for overfitting?
Yeah, so in some senses, yes, but that risk is kind of always there, right? Depending on, even in the past, right? So as long as you are still doing your like loss function, going through a loss function, calculating the loss score, and then, you know, optimizing on that, it's actually arguably more efficient to do it this way because running it through that optimization, it might be easier to get to your solution in comparison to the other ways. And in fact, we kind of know that it is, which is why we prefer doing these types of things with large data as opposed to like kernels and splines. But yes, I would say, yeah, I guess fundamentally because you have more degrees of freedom, I guess you would be at more risk of like, overfitting the model. So you do have to be careful about that. I guess because it's implemented in this regime of like optimizing as per some kind of like loss score function, people aren't really worried about that happening as much, and it's all about trying to get that process as efficient as possible. Okay, so that begs the question, right, which is, how many hidden layers and nodes / perceptrons? Yes.
Like the predictive models where the explanatory and output variables have a relationship, but like it's not meaningful to interpret that relationship with your model.
Yep, that's right. So, you know, I can solve this, and then I would have values, or, you know, I would know what my activation functions are, and then I would know my values for all of my weights, all my W's and all my V's. In the same way that we would know these for like the coefficient values, right? But unfortunately, there is now not a direct translation of our input to our output where it's like a easy transformation where I say, x changes by some amount, and therefore y changes by beta times that x amount, right? Here we would have to say, I changes by some amount, and then you'd have to like track it through all of this stuff, right? So yeah, the interpretability, is really not there. Yeah, so this is very much solidly in the like prediction realm. Yeah. That's why econometricians don't use neural networks as much. I mean, that's a generalization. They're starting to, but. Any other questions? Okay, so how many hidden layers and nodes or perceptrons? Okay, so let's talk about hidden layers first. Number of hidden layers. So this is general advice, right? So if you have no hidden layers, so this would represent linearly separable functions. And I would generally say, if you're going to do this, stick to linear regression or the regression of the functional form that you assume is going to be making the model fit the data. It'll be probably more efficient. Or equivalent. So one hidden layer approximates any continuous mapping in finite space, which is pretty kind of astonishing if you think about that, right? So literally one. Or the combination of two sets of activation functions, one from input to hidden layer 1 to output, can map to literally anything in continuous space. Yeah, very powerful, right? And then 2 plus represents arbitrary decision boundaries to arbitrary accuracy. With correct activation function. So, the question might be, if one hidden layer can get me anything that I want, why would I ever add more than one hidden layer, right? And actually, it's because the path through these activation functions is a sort of big efficiency step. And so adding additional hidden layers can actually make your computational solving of that optimization much more efficient. Depending on, right, the context of the data and what you know about the sort of transformations. And so, when you hear about things like, deep neural networks, you're often talking about things that have 2, 3 plus hidden layers in them. Okay, so you don't need a lot of hidden layers to get to, outcomes that you might be interested in. So number of nodes / perceptrons. So here I would say no real agreed upon method. Some rules of thumb. That people use So size of input layer is greater than hidden nodes is greater than size of output. So this is one procedure that people use. A different one that I've seen commonly referenced. Hidden nodes, you want to be approximately 2/3 of the input plus output layer sizes.
That's actually like the number of hidden nodes, not the number of hidden layers.
Correct. Yep. So if you sum up every node in all hidden layers, you would want that to be about 2, according to this particular method. But I will actually say I'm writing out these methods, and some of them actually kind of contradict each other. They also have hidden nodes is less than 2x the input. And then number of hidden nodes is equal to the number, equal to number of samples divided by alpha times number of inputs plus number of outputs. Where alpha is between 2 to 10. Yeah, so these are like different rules of thumb that different people have come up with. Some of them are more similar, some of them are a little bit different. You know, the context of your problem will drive some of this, but you know, it's worth kind of playing around with it a little bit to see. Very generically speaking, right, more nodes typically is like overfitting because we're technically adding in flexibility, right? But if you're going through these, it's kind of a balance between the nodes and hidden layers and also the parameters which you have control over and the activation function that you have control over. You know, it is still about cross-validation, right? And as long as you're doing that, with these neural networks, you typically have enough flexibility that you could be, you know, a little bit arbitrary on some of this stuff and still get to a good sort of functional fit and a good end product. And again, you know, this stuff may be more related to your computational efficiency and ability to solve for what you're interested in than necessarily, you know, just about this like overfitting stuff, right? And so you can almost think of this as, you know, we've been talking about this thing of model complexity doing total error, right? And so we want our, you know, out of sample MSE, we want to minimize that, right? And so we're doing the same thing here, but now you actually have almost this other objective of model complexity as it relates to like computational efficiency. And whereas model complexity here before was, you know, before ML, we're talking about parameters and model structure. And now we do, with ML, we now also have number of nodes and number of hidden layers. And these things, all of these together are serving to also trying to minimize, or I should say maximize, computational efficiency. Yeah. Yes. Before we jump to R, we will take a break, which is right now, unless anyone has any questions. Yeah.
So for overfitting, we should lower, for example, the nodes and parameters, and we do this with the cross-validation.
Well, I would actually say that, yeah, so the cross-validation is how you avoid the overfitting. And it actually may be the case that you might mess around with the number of nodes and hidden layers to try and do that. But actually messing around with that stuff, it's probably, better to modify those things to help with computation as opposed to this thing, because you've got so much flexibility that minimizing this thing is going to happen sort of automatically, no matter how many nodes or hidden layers that you are adding. But like, you know, an extreme example might be like, if you happen to add a hidden layer, you might cut the computation in half, right? But you would still be able to achieve the same, you know, end results with your out of sample mean squared error. So we definitely still want to be doing cross-validation to do this, but now you have this other thing to think about. Yeah.
Because I was thinking cross-validation might take lots of time for a big data.
Yes, that's right. So, yeah, there might be other metrics and other heuristics that you could calculate if you really are dealing with something large. That could be an alternative to doing like what we've been doing with cross-validation. Yeah. Although I will say, even with pretty large stuff, the validation process is super important. So, you know, cross-validation is not uncommon, even with pretty computationally intensive things. Yeah. All right, break. Hey.
Tomorrow you have available in your office for office hour.
Yeah.
Because I wanted to talk about your comments.
Sure. Yeah. Let's if you want to swing by tomorrow, I'll be there in my office. Yeah. Great.
Yeah, so everybody already signed.
Hey.
For homework 4, we actually have a data site called CC data, but I didn't see it is uploaded in Canvas. So
Oh shoot.
I will upload.
Yeah.
upload
Would you
it.
mind uploading
Okay,
it into the
sure.
assignments? Yeah. Thank you.
I have a quick question about the homework, if that's okay.
Yes.
Yeah, so I'm trying to interpret this first set of graphs. This is for question 1 with the 0 or 1 depending on the median.
Okay.
And at least my thought process was that, I mean, I guess it makes sense that the MPG makes the most, like, there's the clearest division.
Yes.
But I would assume that even these might have some kind of predictive value. I mean, compared to the ones like this where I don't know how to predict this.
Yeah. Well, an engine has a discrete number of cylinders, and then it could be, they were saying it's, 0 or 1, and then they can both show up, right? And so if your variable here is not continuous, it'll look like this. If that makes sense, right?
Yeah. Okay, that makes sense. That's why it's like this.
Yeah.
Then
Exactly.
how should we try to gather if it's going to be an effective, if it's a potentially explanatory, if it's actually a value in a model?
Yeah. So that's kind of what the point of the question is, right?
Yeah.
It's like you want generally the eye test is like correlations, right, between your explanatory variable and your response variable, and so that's one thing to look for. But just more generally, you want you want there to be variation,
Right.
And so if you're able to visualize that variation,
Okay.
that might be an indicator, and a stronger one if you see like correlation in the visualization.
Okay.
Yeah.
I will try with that.
Yeah.
Thank you.
Alrighty. Okay, let's jump on over to R. We're going to use ISLR because it's got a data set that we're going to load. All right, and so we're going to do a data set called default. Let me put that into a data table, and then we can take a look at it. I can't actually quite recall if we've looked at this data set before, but it's a pretty simple one. You've got defaults. So is someone in default whether or not whether or not they're on default on a credit card, whether or not they are a student, and then the balance on the credit card, and then the income of that person. And so it's like this question of whether or not I can predict someone's default status via whether they're a student, and then based on how much balance they carry, or their average monthly balance, and what their income is. Okay? So we're going to investigate that. And I'm going to basically start out by changing these to numeric. Yes, it is. Is that better? Yeah. And we could do this, but I'm just kidding. Default student equals as numeric. So all this is doing is changing the yes and no's into ones and zeros. Okay. All right. And I'll move this down a little bit so that that remains there to be seen. I'm going to scale the data. For everything that's not our response variable. And then what I'm gonna do is divide it into training data and testing data. So we're not doing our like cross-fold validation. We're just going to feed in a set of training data and a set of testing data. So default.train, default.scaled, default.sort. Okay, so this, oh, hang on, what did I do? Sample and row. Ah, 0.7, not 7. Okay, there we go. So if you guys want to see what this looks like, I basically randomly sorted the data such that the training data is like 70% of the original data randomly, and then the testing data is 30% of the data randomly. And you can see that here, default scaled is 10,000 observations, and then I've divided that into 3,000 and 7,000 of the testing and the training. Yeah, basically, I sampled equal to 10,000 from 1 to 10,000, and I sampled 7,000 times, which is the number of rows times 0.7. And then those are the indices. I sorted them, and then I put them in my index operator, so that from default scaled, it returns only the ones that were drawn out of my sample, and then minus this, which means everything else. Yeah. We are going to use a library called Neural Net. Default neural network. Or I should say, not default, default neural network, because it's referring to whether or not you're in default. So we're going to regress default on everything else, which is just those 3 other variables. The data is going to be our training set. Okay, so hidden is the way that I specify the number of hidden layers and the number of nodes. So the way this works is for each number in this vector, it tells you how many nodes there should be in its corresponding hidden layer. So this has, because there's 2 entries, this will have 2 hidden layers. The first layer will have 2 nodes, and the second layer will have 3 nodes. I'm going to use a logistic activation function. And we'll run this. Okay, so you guys, if you guys were watching, oh yeah.
Sorry, how do you know how many layers you have?
It's arbitrary, right? So we're we're choosing based on kind of rules of thumb at the beginning, and then I can modify it to try and increase the like computational efficiency.
And I would just add on to that.
If you wanted more hidden layers.
Gotcha.
Yeah. I wouldn't do more than, if you're playing around and you're starting off just doing stuff like this, I probably wouldn't start with more than 2 at a time. Yeah. Yeah, unless you're really into doing some like deep learning stuff. Yeah, probably 2 layers is more than enough. I don't know if you guys were watching, but this actually took about 10, 15 seconds to run, right? And it's a pretty small model. So right now I'm not like doing this very efficiently, because it's so small. If we do summary of default.nn, you can see here all the stuff that I'm able to get. I can get like the covariance matrix. I can get all of my weights here. 1. Yeah. But probably the most interesting thing to see. Okay. Okay, so this took about 7,500 steps to optimize, with a total error of 73. You can see on each edge we have the weights associated with these, and so I could actually go back in and and actually figure out, I'd be able to calculate manually based on any set of inputs, what my output would be. Okay, and then you can see we have, as I was saying, we have 2 hidden layers. The first hidden layer with 2 nodes, the second hidden layer with 3 nodes.
And what's the blue?
What's the blue values? Those are the let me see. Is it the value of the where is it? No, because that would depend on the input. What are those values again?
Just the weights that the layers have, I don't know.
No, the layers themselves are not going to be weighted. Yeah, actually, I'm not sure about what the blue values are. I will get back to you on that. Okay. So we can take this. This is kind of like our finalized model that has all of the weights associated with it. And I can use the model, right, to do predictions. We don't use the predict function. We actually use a new function with neural net, which is called compute. And so, for example, I can take my model and then do predictions based on that test set. Okay? And if I take a look at this, how do I view, result. So this gives me a vector of the predicted outputs. You'll notice that these are not as zeros and ones. We had it as like a logistic function output, right? So these you can think of as the probabilities associated with particular outcome. So what I could do is default.test I'm gonna add in a new so in the test set I'm just gonna stitch in a new column called probability, which is what we just looked at. So that's net results. And I'll use that to make a prediction on whether or not someone was in default. And kind of in the same way that we talked about with logistic regression, basically I'm going to say if the probability is less than 50%, I'm going to say that they're not in default. And if it's greater than 50%, then I will predict that they are in default. 0.5, so 1, 0. Boop. There we go. Okay, so our overall out of sample mean squared error is so how do we calculate this? This is our observed minus our predicted squared divided by the n, right? So default.test $default, this is what we observed, that's the real data, minus default.test $predict, and then I'm going to square this thing, and then divide by the number of rows.
This is different than a test MSE?
This is the test MSE. Yeah. Okay, so the test MSE, right, of this particular model has a 2.6%, or it's, well, because we're dealing with 0 or 1s, I can say, right, that this has a 2.6% error rate, right? So it's getting the answer wrong 2.6% of the time. So is that good or bad? So this is where you guys have to be careful, right? So this, it's context dependent because we don't know how well the data is balanced, right? So let's say 26 out of every 10,000, let's say you only observe 26 defaults out of 10,000 observations, right? If I just predicted no default, I would have a 2.6% error rate. Did I do that right? Or is it 1,000, not 10,000, right? I would have a 2.6% error rate. And so let's look at this. So if I do table default dot test $default. So I have 100 people who defaulted and 2,900 people who didn't. So 100 over 1,000 or 3,000 means only 3.3% of people have defaulted, right? So if you guys remember, if you do this in like a confusion table, confusion matrix, I could look at our false negative rate. Not here. I can look at our false negative rate, which would be the same thing, except I only care about when my observation is larger than my prediction. And so that'll be something like this. Divided by n row default dot test. So the number of times that I false negative, the number of times that I predict someone has defaulted when they didn't default is 0, right? And then, but my false positive rate let me just copy and paste this thing, and all I need to do is change the sign here. Is that right? Yeah. Oh, wait a minute. Greater than, less than. Why is it both 0? No. Well, we know that can't be right because they have to sum up to the MSC.
Should it be predict, not prediction?
Ah, yes, thank you. Okay, I'm going to take back everything I said so far. There we go. Yeah, so in this case, we have a much larger false negative rate than our false positive rate. And if you were to look at based on the balancing, right, you could actually look at the proportion of that particular subset of data that is getting predicted correctly versus not, and it's going to be a lot larger because you have such unbalanced data. And so you could calibrate your neural network to favor one of these things more than your mean squared error, in which case you might have a model that may have an overall worst mean squared error, but might do a lot better at your false negative rate or at your false positive rate, which is something, right, that we've talked about why you might care about that. Yeah.
Sorry, where did you fix it again?
Oh, I wrote prediction instead of predict, which is not a, actual column in the data. So yes, thank you for catching that.
Surprised it didn't yell at you about that.
Yeah, me too. I guess if it's less than or greater than a value that doesn't exist, you would think it would throw.
Missing value is 0 or something.
Yeah. Darn you are with your error catching. Okay. Great. Any questions about any of this? Okay.
Is the line of code that you wrote to make the numeric value for student, it was just copy and pasted from default, right? And then you just change default to student.
Where?
Default, when you're making the yes into numeric 1 or 0s.
Oh, yes. Yeah. Right up here. Yeah. Right at the top.
Oh, I see why.
Okay. Anyone else? Yes.
Could you explain a little bit about the beginning you scaled all the prediction data, the reason why? Is that necessary for us to do the neural net regression? We need to scale all the prediction.
Not always, but sometimes it can make the optimizer operate better. And the reason for that, so people don't always have to scale, but it's often a good idea to do so when you're doing things like gradient descent or other sort of like derivative-based optimization solvers. The gradient that's created when you're doing these derivatives can be affected by the scaling of your data. And so if data across different dimensions are really different in orders of magnitude, it could actually cause the solver to be less efficient because maybe it's like the way that I might think about it is like if you have like a hill, you if you're thinking about it in like 3 dimensions, you want to walk down the hill basically, and if it's scaled inappropriately, you know, one direction might look really flat and one direction might look like much steeper drop off. And so if the end target is like over to the door, you know, I might be going this way a lot more because of the scaling of the variable as opposed to, you know, heading that way, right? And so it's often a good idea to do scaling now that we're getting away from our analytical solution and doing these optimizers. But you know, on the other hand, I will say a lot of these optimizers are like very well made, and probably a lot of them can handle unscaled data pretty well. This is just me trying to be safe. Yeah. Yeah.
Is it possible that we get different answers, different numbers?
Yeah, because we're doing random sampling of the training and testing set, so hopefully not too different, but yeah, it could be a little bit different.
0.0253.
That's pretty close, right? Mine was 0.26, so we're off by 0.0007. Okay, any other questions? Okay, great. Yeah, don't have time to talk about convolutional neural networks, but we'll hit that next time. Okay, see you guys next week.
So you know class on Monday?
Yes, that's right. I'll see you guys in literally 1 week. Yeah, just a reminder, Monday is Memorial Day? Yes. So holiday, no class. Yeah, give me 1 sec.